And then
Okay, so we're maybe going to go ahead and get started with our afternoon tutorials on the immersed boundary method and IBAMR. So we're very excited to have Barrett here to give us the kind of overview of IBAMR and to get us started. He's currently at University of Utah, soon to be moving to College of Charleston. Yes. Okay. And I think based on yesterday for questions, people had said they couldn't hear things. So we do want to try and pass around the microphone. So when there are questions, please wait for one of us to give you the microphone. Thanks.
All right. We're going to talk about immersed boundary. So I want to temper some expectations first because IBAMR is complicated and building it, as some of you have experienced, is kind of challenging. And so what our goals for today are, one, to get an introduction to immersed boundary, primarily so that we have a shared language to ask relevant questions and perhaps hopefully communicate easier to each other. Give you an introduction to IBAMR, kind of the design philosophies, how we build examples, and then we'll also run some examples and visualize IBAMR output. And so, yeah, we'll get a basic understanding of the design, example layout, or input file, and hopefully you will be able to use this as a basis to start exploring and considering your own implementations. What you should not expect is expertise in IBAMR. I've been working on this for about a decade now, and I feel like I don't understand all of it. Should not expect to be an expert in C++. We actually won't talk very much about C++ at all. And then visit the visualization tool we'll be using can be kind of complicated and hard to use sometimes, and we will not be an expert in that at the end of this. With that in mind, I have a collection of simulations that people have used over the years, from locomotion for eels or jellyfish. I don't know if Alex is here. That's his simulation. And it's also had a lot of use in cardiovascular simulations. So recently, Boyce and company published their heart paper, which has been, I don't know, years in the making, decades in the making. Couple of years in the making. And so at the end of this, maybe you can put together a simulation like this. Maybe. So if we want to talk about immersed boundary, we're going to start at the very beginning. And so we need to understand a difference between Lagrangian and Eulerian variables. So in a Lagrangian frame or a reference configuration, we label fluid parcels with some label, call that capital X. And we keep track of how that fluid parcel moves. And we do that with our mapping chi. So this chi mapping tells us where the current location of a fluid parcel is. If we want to know the velocity in a Lagrangian frame, we can just take the time derivative of that mapping. So that's pretty easy, d chi dt. And in an Eulerian frame, we're working in a current configuration, we have a spatial coordinates are fixed. And so we just talk about a fluid velocity or a velocity field at those locations. We can map between, or we have a fixed Eulerian velocity. If we want to know interchange between the velocity in a Lagrangian frame and the velocity in a Eulerian frame, then what we have to do, well, our velocity in a Lagrangian frame is our time derivative of chi. We can just evaluate our velocity at the current location of the structure. So writing that in a slightly different way, we can convolve our velocity field with a delta function so that we can pick out a particular velocity field. And this is kind of our key idea that we have in our immersed boundary method. So we will be tracking our structure in a Lagrangian frame, and we'll be reading off Eulerian velocity fields. using this delta function. We can also talk about rates of change of certain variables. So if we have a scalar variable and we're tracking this in a Lagrangian frame, then a time derivative is just our regular partial derivative with respect to t. Since our fluid parcels are fixed, our labels are. But in an Eulerian frame, it's a little bit more complicated because we have to worry about how things are moving in that frame. And so when we try and take a time derivative of our Eulerian scalar field, then we have to use our chain rule, and out pops a velocity gradient, or not a velocity gradient, a u dot grad term that represents how things are moving along our fixed frame. So following up on this, we can define acceleration of our fluid in two different ways. Second derivative of our velocity field of our position mapping in a Lagrangian sense. In a Eulerian sense, we have to talk about how velocity is being transported in our Eulerian fixed coordinate system. We'll also need this notion of the deformation gradient, which is our derivative of our chi mapping with respect to the Lagrangian coordinates. We can think of this as mapping line elements and a reference configuration to line elements in a current configuration. And we will eventually be using this to talk about structural mechanics. So as an example, we can consider a cube that's being sheared. If we shear the top of this cube, we can very, very easily compute a deformation gradient. Perhaps a more relevant or more interesting example is a cube that's being stretched, so it's being extended in some ways. So we take a unit cube, you extend its sides, you can write down that deformation gradient. But if you want that to be an incompressible deformation, then you need the volume to stay constant. And so after that deformation, you need the product of how you've extended at lambda 0, lambda 1, and lambda 2 to be 1. And more generally, if we want to talk about how our volume is being changed by a given deformation, we need the determinant of this deformation gradient. This is what gives us, this is what measures volume change. So you can write down an ODE for how the Jacobian changes, and it has this nice divergence of hue that pops out. And we are incompressible. We need our Jacobian determinant to stay 1 at all times, or equivalently, we need our divergence of hue to be 0. We also need to talk about how materials respond to strain. So we can measure strain using our deformation gradient, but if we want to know about how that material responds to strain, this is what we call the stress. And so we can compute a force on a surface or the traction by taking the stress and dotting it with a normal. And if we want the net force on some surface, then we need to integrate the traction over the entire surface. Different materials will come down to different specifications of how we compute the stress. So you need some kind of relationship between the stress and the strain, and that will be determined by whatever model you're trying or you care about. So we can come to conservation equations. So for conservation of mass, we can take some volume of fluid, we can take some that has some associated density, you integrate it over the volume, take a time derivative, and in order to take that time derivative, since our volume is moving, we convert it back to a reference configuration, interchange our integral and our time derivative, do a bunch of calculus, convert back to a current configuration, and this gives us a conservation of mass equation that must hold pointwise. And so we can interpret this a little bit. So this tells us our first part, d rho dt, that the density is traveling, being advected by our fluid, and then it can change according to how our fluid is compressing or expanding. our fluid is incompressible, and we just have the rho as advecting with our fluid. And that gives us conservation of mass. For our momentum equation, we can define our momentum in a similar way. It's just our density times our velocity integrated over our volume of fluid. We can play the same kind of game where we take a time derivative, convert to reference configuration, do a bunch of calculus, we convert back. And in the special case that we have, and in the special case in which our velocity is divergence free, we're left with just rho times the material derivative with respect to time. Oh, this is also if rho is constant or density is constant. So we're making two assumptions here. One, our material is incompressible, so the divergence of U is 0, and two, that our density is constant. If we don't want those assumptions, then you have to do something else. You get extra terms that show up. So if we want our end momentum equation, we look at F equals ma. So we need the rate of change of momentum, which we just computed, and we need all of the forces on our fluid, which can consist of external body forces like gravity, or our internal surface forces that are coming from our stress tensor. So combining those and using our favorite divergence theorem to convert our surface integral over the traction to a volumetric integral, we get our momentum equation. The thing that's left here is to specify our stress tensor. We need to specify our material. And here we're assuming a Newtonian flow. So we'll take our stress, decompose it to some pressure term and a deviatoric stress that just changes our volume. Or sorry, does not change our volume. And the Newtonian assumption here is that the deviatoric stress is linear in the rate of strain and the fluid is isotropic. So there's no preferred direction. The rate of strain here is defined as the symmetric part of the velocity gradient. And if we do that, then we get back Navier-Stokes equations that we have been using. Now, with this particular assumption that the velocity is incompressible, here's our conservation of mass condition. We can rewrite this divergence as a gradient of pressure and viscosity times the Laplacian. So we have fluid equations. Now, if we want to talk about an immersed boundary, some structure that exists in our fluid, we will assume for now that it's infinitesimally thin and massless, which are assumptions that we can derive methods that do not have to satisfy this assumption. But for now, to simplify things, we can just make sure it's infinitesimally thin. In that case, we want to know how it moves. We have an Eulerian velocity field. We can interpolate that to the structure or convolve it with the delta function to read off at our structure's location. So this tells us what the velocity of our Lagrangian structure is. As it moves, it's going to undergo some kind of deformations. And so generally, for the stuff that we're going to talk about here, we're assuming that a structure is elastic. There's some elastic energy associated with those deformations. And so you can compute those forces by getting an appropriate derivative of that elastic energy. And so an example that I think is fairly common in immersed boundary methods is an energy associated with tension in the structure. And so this energy is minimized when, if we have a parameterized structure, this energy is minimized when the tangent vector is magnitude 1. And so we can determine forces that are associated with this energy by looking at perturbations of the energy. And you can do a bunch of calculus again to compute the forces. And it's not pleasant. So generally, you just look up what the forces are that somebody else has derived for you, because that becomes easy. And so in this case, you can get forces associated with with that energy that looks something like this, which we will discretize in a little bit. So once we have those forces, we need to do something with those forces. And we have a momentum equation for our fluid. So we can take our Lagrangian forces and evaluate them on our Eulerian grid by, again, convolving it with our delta function. And this takes our Lagrangian forces, puts them on Eulerian grid, and then we can apply them to our momentum equation. And so this is our full immersed boundary method in all of its glory. We have, again, our momentum equations. Our first one, we have divergence of our stress. The stress needs to be defined depending on what material we care about. For the first part of this, we will be assuming it's Newtonian. We will get rid of that assumption near the end. We have conservation of mass, our second equation, where the velocity is incompressible. And we have our structure as moving at the local fluid velocity. So we interpolate our velocity to the structure. Those deformations result in forces from some elastic energy or from some other model that we might care about. Those forces then get applied to our momentum equation, coupling everything together. We have our equations, we need to solve them. So we can talk about solution strategies. And the one that we will be employing, and that is employed most commonly in IBAMR, is that we will be using an explicit method for our structure and an implicit method for our fluid. And so the key components that we have to be able to do to implement an immersed boundary method is one, moving the structure. So we need to be able to read off the fluid velocity at a given location. We need to be able to move the structure at that velocity. We need to be able to compute forces from the structural deformation. Once we have those forces, we need to be able to evaluate those forces on our Eulerian grid. However, we've discretized the fluid equations. And we also need to be able to solve the fluid equations. And so these are all somewhat independent things that you could use any fluid solver, any Lagrangian structure discretization that you might care about. You just need to worry about how they're coupled. And so I will tell you about how IBMR does that. We'll start with the Navier-Stokes equations. So we need to be able to solve the fluid equations. We typically use what's called a MAC grid. So we store velocity components on the faces of the grid that are normal to the velocity. So we store, for example, the horizontal components on the X faces and the vertical components on the Y faces. And the pressures are stored at cell centers. We can discretize our operators however we might want. What we do in IBMR is we just use second order finite differences. The advective term is a little bit more complicated. We won't talk about that today. But you have discrete operators and some capacity. We write down, for example, a forward and backward Euler scheme. We treat the advective term explicitly. We treat the immersed boundary forces explicitly. We treat pressure and viscosity implicitly. We do that, then this results in a linear system that we have to solve. And you can solve that linear system however you might choose. In IBAMR, we use a GMRes algorithm provided by Petsy with different preconditioning schemes. But if you have to solve a problem and you go to this in MATLAB, you could just use backslash. Or you could use a projection method if you wanted to. So again, there's a lot of freedom with immersed boundary methods if you choose not to use IBMR. So we have a way to compute the fluid velocity. We need a Lagrangian discretization. So we typically use point clouds in IBMR or finite element meshes. Those are both. We typically do things. I don't think there's anything else that we do. I guess NIT has, there's some support for level set methods as well. But I don't think any, what are you talking about? Level set? No level set methods. Forget I said that. So we treat the structure as a point cloud. You can treat, what? Oh, yeah, but that's also a point cloud. So you can discretize the structure as a point cloud or a finite element mesh. We'll go over both of those kinds of examples. And then we discretize the forces associated with that. You can just use center differences. But again, if you're using some finite element method, you might discretize your Lagrangian structure or your Lagrangian forces in a finite elementy way. I won't talk about that. Be wasteful. Then you time step it. The kind of key things here are the interaction equations. How do we go from our fluid structure to our Lagrangian structure? So how do we interpolate velocities? How do we spread forces? And we do the same thing that regularized Stokeslet does, and that we replace our singular delta function with a regularized delta function. And this is where we have a key difference between immersed boundary and regularized Stokeslets. With regularized Stokeslets, we need to choose a delta function such that we can evaluate the Green's function with some caveats. For immersed boundary, we have a lot more freedom in how we choose a delta function. Typically, we choose one that has compact support so that we can efficiently evaluate the integrals. I have several examples and they all look very similar, but it turns out, we will see this in a little bit, that they will provide drastically different errors. Some of them will be very accurate, some of them will be terrible. But you can choose your favorite delta function if you don't care about accuracy. Once we replace our singular delta function with a regularized delta function, we can use quadrature to evaluate the integrals. So something simple like trapezoidal or midpoint rule tends to be sufficient here. And so we replace our integrals with finite sums. These sums are finite because our delta function has compact support. An important thing to note here is that when we're spreading forces to the background grid, we have to worry about the dimensionality of our structure. And this is something that will show up when we talk about the details of IBMR, is that here I'm assuming the structure is infinitesimally thin. If it has an area associated with it, then this will become an area element, delta x squared. If there's a volume associated with it, then it needs to become delta x cubed. So the scaling factor depends on the dimensionality of the structure. And then we'll come back. There are questions so far about immersed boundary?
I have a question.
Yeah.
Sorry, this is not my area, but when you use this immersive boundary equation, you are talking about low Reynolds numbers?
Any Reynolds number. So we can do high Reynolds numbers, we can do medium, any Reynolds numbers will work.
But when you use this equation, you are talking about laminar flow or turbulent flow?
Well, the examples that I will show are laminar flow.
Okay.
But you can, in principle, do turbulent flow.
Okay.
There's a question of how do you put in turbulence models that I think is an open question. How do they play with immersed boundary methods? But in principle, it works.
Yeah, it's only because I used it for laminar flow and in turbulent flow, it's a little more complicated.
It is a little bit more, just a little.
Yeah,
But
yeah. No,
yeah, I mean,
let me
there's-
say that it's a bit complicated. Yeah. Yeah. Thank you.
Other questions about immerse boundary simulations? We've got another. Oh,
I know you said you weren't going to talk about the adaptive terms in IBM. Say a few words. Are you guys doing some kind of upwinding?
there is some kind of fancy upwinding going on. So we have a few different discretizations. There's a ppm based discretization, piecewise parabolic,
Okay.
that I think is most commonly used.
Okay.
The one I like is a cubic upwinded interpolant.
Okay.
But there's several different discretizations that we have in place
Okay. So there is.
that are upwinded.
Yeah.
Or center differencing for. There's also center differencing if you or centered skew symmetric differencing if you want to maintain certain kinds of energy properties.
Thanks.
All right. Let's talk about IBMR. So IBMR is a lot of things. Some of these things might be a lie. It is MPI parallelized. That is not a lie. Last I heard, it was scalable to hundreds of cores. I don't know if that's been improved at all.
I think hundreds is probably about right.
Hundreds is about right. Hundreds is about right.
Maybe thousands.
Maybe thousands. It is adaptive, so you can adaptively refine the mesh to tag cells based on where the immerse boundary location is, based on vorticity, based on where you think you need increased levels of accuracy. And it can use a coarse mesh away from those areas to make it efficient. It's generalizable. So we have support for several different fluid models. We have support for multiple structure types, finite element meshes, point clouds, different elasticity models, different structural models.
Yeah, can I just ask a question about the adaptivity?
Yeah.
Your comment.
Sorry.
Can you hear me? Yeah. Okay. So you're adapting the fluid grid, the
Yes.
Eulerian grid.
Yes.
Is there also facility to track like your surface or your immersed surface when the mesh quality is degrading? Like you said, you can discretize it using finite elements. Do you have finite element mesh quality measurements that you're tracking and then can update that discretization as well?
As far as I know, no. But
So sort of. I haven't run into any cases where it's been clear that you need to do adaptive meshing for the structure. But one of the things that we've been working on over the last couple of years is to integrate the DEAL2 finite element library into IBMR, and that's not yet publicly available. Hopefully it'll be publicly available in the next year or so. And DEAL2 has vast support for finite element adaptive mesh refinement. And one of the things that we'd like to do is to have something like an adaptive structural discretization, but it gets a little bit complicated because you kind of have to choose the structural discretization to correspond to the fluid discretization that you want the structure to talk to. You can't choose those to be independent from each other as far as I know. I used to believe that you could, but I was wrong.
Alex.
Okay. Well, get this back to voice anyway. So turn it on. Oh, yeah, there's that. Okay. I think this is a little bit niche of a question. But I know that there's like finite element nodal representations and finite element quadrature representations for the exchange. Are the quadrature points adaptive or is it based off the structural deformations?
I'll talk about this.
All right.
Advanced description.
You're asking too advanced of question.
A niche question.
I'll talk about this later.
All right, I'll just keep it.
So now we get to the lying portions of IBAMR is it's easy to install. So, and to be fair, when I wrote this, every system that I had used auto IBMR on, it just worked. I do not have a Mac, so apparently Macs are still, the support for that can be questionable sometimes. It can be a pain sometimes to go through, but it can be done eventually. It's also easy to use, and this is where your mileage may vary, because if it's similar to a pre-existing example, if what you care about, what system you want to model is similar to a pre-existing example, then it's not that challenging to modify that example to do what you want to do. If your example or what you care about, your system that you want to model is not a pre-existing example, then it can be challenging to put in. And that's where the developers are reachable. And I think that they are very nice and pleasant people to talk to, but I might be a little bit biased. So let's try and use it. Again, with the immerse boundary method, so the things to keep in mind, we have kind of three key things that we have to be able to do. We have to be able to solve our fluid equations. We have to be able to solve our structural equations. And we need to be able to evaluate our coupling operators. So we need to be able to thread and interpolate forces. And so to help with that, we have kind of four key principles in IBAMR. There's a patch hierarchy object and associated objects that manage our adaptive mesh grid and the data layout and the data associated with the Eulerian grid. We also have integrator classes that know how to solve certain equations. So they know how to solve Navier-Stokes, they know how to solve IB, they know how to solve advection diffusion equations. And then we have different objects, different classes that are associated with different immerse boundary models, a way to evaluate forces in different ways. And we'll see a few of those. And then there's an input file that is parsed and provides a bunch of runtime options. And so we're going to look at our first example, which is, I mean, we're basically going to recreate this movie that's been playing nonstop. And this corresponds to a stretched elastic membrane. So it's kind of the first example that most people do with IB methods. You can think of it, the way we discretize it, you can think of it as we're taking a discretization point cloud, we're applying 0 rest length springs in between every point. So there's some tension associated with this membrane. And then we're going to deform it, and we're going to let it go and see what happens. So we need to open up IBAMR. So I have built auto IBMR and just this directory. And so the source files are all located in TMP. And so there's 3 directories here. There's a build directory, there's a source directory, and an unpack directory. So we're going to look at the source code for this first example. And just as a reminder, this is IB/explicit/EX1. So we're going to go into the source directory, which is IBAMR-0.16.0. And here, there is an examples directory. So we'll go into the examples. And this is where we have lots and lots of examples, where if you can figure out how to run them, they might do something. And I'm here to tell you how to run them. We want to go into IB. We'll go to IB explicits EX1. And so there's a lot of files in this directory. The one that we will care about for now, we'll talk about the others eventually. The one that we want to look at is example.cpp. So this is the source code for our example. Sorry, I'm going to navigate all the way to the top so we can go from the top to the bottom. This is where, if you aren't familiar with C++, you might be a little bit lost, and I'm sorry. We have a limited amount of time, so I will try and explain the high levels as well as I can. So the key features here that I want to point out, there's a main routine. This is what's being executed whenever we run our IBAMR example. The key things are, let me set line numbers. So I'm going to add line numbers. The key things start at line 199 or 99. So we have an object that is an INS hierarchy integrator. So incompressible Navier-Stokes hierarchy integrator. This class knows how to solve the Navier-Stokes equations. So that's one of the things that we needed to do. We needed to solve Navier-Stokes. This object will do it. And so we create an object of this type. The other key thing, line 123 to 127. So we create this IB hierarchy integrator. This knows how to solve our IB equations. What it requires is some way to solve Navier-Stokes. And so we give it the Navier-Stokes integrator. And so this will spread forces to the Navier-Stokes integrator, and it will interpolate velocities from the Navier-Stokes integrator. The other key object, IB method ops. This is defined right up above. And this is how we compute our IB forces. This is what gives you the model to compute forces. So this IB method knows how to do point clouds and kind of what you might consider traditional immerse boundary methods. And I'll show you a little bit more examples of what those look like. But these lines are kind of the most important parts. Sets up our fluid solver, sets up our IB, our immerse boundary solver. The next few lines creates our patch hierarchy. So from line 128 to 143, this is how we determine how we're going to refine our grid, where it's going to happen, and how we store all of our Eulerian data. So I mentioned a patch hierarchy that actually exists on line 130. The next few lines, where we actually configure the IB solver. So we do a few things. There's the IB standard initializer. I will come back to this. There is an IB standard force gen. So this is the model that or the implementation that computes our forces. And IB standard force gen has a couple of different things. I'm going to switch back to the slides to show you what it does. I need to go through these. So it has standard support for many standard elastic structures. So for example, you might consider springs in between forces. So this is the kind of the elastic tension energy that we derived earlier. You can also have support for beams. So you can try and hit a prescribed curvature between points. And then there's an important thing called target points that we can use to prescribe motion. So target points look like a spring that we tether to some prescribed location. If you look carefully at these and stare at them for long enough, you might see that these look like derivatives. Right? For the spring forces, we take differences in locations. But what's missing here is delta x. We're not dividing by a discretization. If you look at the beams equation, this looks like a second derivative. And then we have other forces that also kind of look like a second derivative. So beams have a fourth derivative associated with them. This is a discretization of a fourth derivative operator. But again, we don't scale by delta x. And this is important. And it goes back to what we said about spreading. So when we discretized spreading, we had an area element associated with it, or a line element associated with it. I wrote down as delta x, but if you have area, it'll be delta x squared, volume delta x cubed. In IBMR, at least for these models, we don't know what kind of structure you have. And so you need to make sure that you account for all of the scaling associated with in these constants. And that is done, I think, in all the examples that are presented. I hope so. That'd be bad. Yeah. Okay. So the rest of this, the example.cpp does what it says it does. So I'm not going to go too much detail, mostly setting boundary conditions, which I have not talked about at all. The next important part starts at line 242, where we start our time loop. So we're looping through, or we're time stepping now. And on line 253, we tell the IB equations to advance hierarchy, to solve the equations and advance by some time step. And then we advance time. And we do other things on occasion, like print out visualization files, print out their files. But this is the basic structure of almost all IB-AMR code. We set up some IB associated objects. We register them with the appropriate thing. We set up any kind of boundary conditions, initial conditions, and we time step loop. So there's a couple of other things we need to build. The input file. So there's several different input files. We're going to look at input 2D. So input 2D defines all of our runtime constants. So we can set a domain size. We can set fluid viscosity, fluid density. We can define how many points that we're using on our domain. A lot of these things are commented. There also are options that are undocumented as of now. But so it goes. You can set delta functions. You can set time stepping types. So here we're using Adams-Bashforth for our convective term. I don't think it says it anywhere, but we use an implicit trapezoidal rule for our viscous terms. One of the questions I was asked, we're using ppm as our convective operator. This can be changed to several different options. Defines boundary conditions. Another important part that I want to point out, the IB standard initializer. So this is what's going to create our structure. So we define one structure, and we call it curve 2D64. So this is our curve. It's associated with 64 because this is an input file that we created for a 64 squared grid on our Eulerian domain. And then we have some other lines that put that curve on a specific level of refinement. So in this, to start off with, we have one level of refinement. So max levels is 1. So we're using a uniform grid. So we put it on level 0. And we're also telling it to use a uniform spring stiffness. So when we run the code, IB standard initializer is going to look for files that have a base name of curve2D_64 and parse those files. So this tells us our next important parts. We can look at curve2D_64, which we have 2. We have a .spring file and a .vertex file. The vertex file is what you might expect. It just lists all of our points. We have the number of points associated with this file, and then it just lists all of the X and Y coordinates. The spring file contains the number of springs that we have and what Lagrangian points we're associating that spring with. So this creates a spring between point 0 and point 1 that were listed in the vertex file. We have spring constant associated with them. and a resting length for that spring. So this has some spring constant and a 0 resting length. Then we do that for 0.1 and 0.2, 0.3 and 0.4, so on until we get back to the first point. So the last line here, it's a spring between 0.303 and 0.0. So we're creating an elastic band of points. And that's the spring file. So now, that was fun. Let's run it. So we go back to these IBMR directory where we built things. We go into the temporary directory. Now we look at build, the build directory. We go into version 0.16. I don't know why this one wasn't labeled with IBMR, but that's how it goes sometimes. And so now we see our examples directory here. So this is where we have built IBMR. And we want to build the IB example EX1. So we type make IB EX1. Hope I haven't messed anything up. It should compile the example. Taking a lot longer than I thought it would. Oh, it's just gonna hang out there. Any jokes? No.
You had a spring stiffness in the input 2D, and then you had
Yeah.
springs. Which one overrides which?
So anything we put in the input file will override what's in the .spring file. So we can actually go in that. Oh, so it built. So now we can navigate to the examples, IB, explicit, EX1. Everything in there that was in the build directory is now, or in the source directory is now in the build directory. To these points, we specified a uniform spring stiffness. This is actually overriding what was in the .spring file. But it turns out that those values are the same. So in this case, it didn't matter. So now we have a main2D file. We have an input file. We can run main2D /main2D input 2D. We hit enter, and away it goes. So this one won't take very long. It's already halfway there. Now we can visualize things after it's done. So our visualization tool, most of the people I know use Visit. You can also use ParaView, but I don't know how to use ParaView, so I don't use it. So you can open up Visit. And we want to open up our visualization files. So in our directory, we now have a viz _ IB2D folder. And this contains all of our visualization files. So the dumps.visit stores our Eulerian data. The lag data.visit stores our Lagrangian data. So we can open up dumps data, and we can plot things with a pseudo color plot, for example, pressure, velocity magnitude, velocity components, vorticity, whatever you might, well, whatever's shown up in here, I guess is the only thing you can plot. If it's not here, you can't visualize it. So you need to make sure you specify things that you want outputted, and I will demonstrate that later. But we can just plot pressure for now, but also open up the lag data.visit file. We can now add a mesh. So we'll add curve2D 64 mesh. So this is denoted by all the springs that are associated with our points. So if we add that, it's going to ask us to correlate a database, which we will say yes, because these things were time stepped together. So we do that, and that flat curve is really hard to see. So we go in here and we increase the line width to make it a little bit bigger. And now we can press play, and away it goes. Do things like plot velocity vectors. So I'll pause this. You can plot vector. Oh, you have to make sure that you're on the right active source. So again, dumps.visit to Eulerian data. So you can plot U, which is our velocity vectors. And you can see them change in time. Okay, so that's great and all, but I wanted adaptive mesh refinement. I was promised adaptive mesh refinement. I hear you say. So let's go back to our input file. So we want to add in adaptive mesh refinement. So how do we do that? We go back to the very top. There's a parameter here that said max levels. We had 1. We want to add adaptive mesh refinement. All we need to do is change that number from 1 to, say, 3. So now we're going to be using 3 levels of refinement. Each level of refinement has a refinement ratio of 4. To save my computer, I'm going to make that 2 so we can actually run this. And then I'm also going to decrease the coarsest level of points to 32 because I want to run this. Now we made our Eulerian grid finer. We also need to make our structural grid finer. Make sure that there's no leaks. I guess I didn't talk about that. Sorry. So we want to make our, let's go back up. Our finest grid is now using an equivalent of 32 times 2 times 2 points. So that's a total of 128. So we want to use a structure that's based on a grid size of 128 squared. Fortunately, that's where all of the other curve2D files came from. So we just have to change curve2D 64 to curve2D 128. And that will now read the curve2D 128 files. Yeah.
I have like a dumb general question. I'm probably pretty loud. Dumb general question.
Sorry.
Dumb general question. With AMR, can you do like a Richardson extrapolation or something with the different levels of refinement? Is that a thing?
In theory, we have not set that up. And I don't know if that's something that VoiceOver intends to support.
So the AMR capabilities of the software are based on this library called Samurai, and Samurai does have a Richardson extrapolation based error estimator that you can use, but we don't use it because you have to basically run twice as fine as you actually want to compute on to do the error estimation, and so it's not been something that has seemed practical. But I mean, and there's support to do that kind of thing in the AMR support library.
And just following up on that, the way that is set in this code is by the tagging method and standard tag and initialize. We set things up to detect gradients, which in our case is IB locations.
Yeah, so we usually use what's called feature detection, and the features that we look for are where is the structure. Usually, you need the highest resolution where the structure is. I can't think of a case where you wouldn't want to be using the highest resolution. Well, that's not true. Never mind. Anyway, but usually we want to use the highest possible resolution to capture to the extent we can, boundary layers, for instance, at the structure. So you usually want to have high resolution where the structure is. And then if you've got flow features that the structure generates, you can usually do a reasonable job of by just looking at vorticity magnitude or something like that. And so you can set those things up, but it does require a little bit of manual tuning. So we don't have anything that will actually give you like a guaranteed error or something like that.
All right. So we changed the max levels and the grid. I'm just going to run this so we can visualize it. It's going to take a lot longer to run because we've made it finer, but not that much longer because we're using adaptive mesh refinement. So we won't run this all the way to the ends. I'm going to exit out of visit really quick and open it back up. So this is probably good enough to show the first few time steps. So we open up visits. We do the same thing. Go to the viz directory, open up dumps.visits. And now the different levels are shown. And so if we plot the AMR mesh, you can see the different levels of refinement where they are located. And again, I'll open up the lag data.visits. Curve. Make it a little bit bigger. We don't have very many time steps, but you can see the mesh as it changes for the first 5 time points.
Question.
Yeah.
So how do the IBMR folks feel about having a symmetric problem and then the mesh refinement's not symmetric?
We can't hear.
Oh, so she asked.
Us. Annoying question. Here's an annoying question, and I just want to know what the current thought is if having a symmetric problem and the mesh refinement is not symmetric.
My thought is, I don't care. I'm fine with that. This might have a more detailed, nuanced.
So the way that I would think about it is that if mesh asymmetries are dominating your dynamics, that you are way under resolved, and that you need to be using a finer mesh. It's pretty hard with the kind of adaptive mesh refinement that is implemented in Samurai to guarantee that symmetric structure configurations give rise to symmetric locally refined meshes. There are other grid generation algorithms that could do it that if people really care about maintaining symmetry, I think wouldn't be that hard to implement. But yeah, I think the main thing is that if you get results that are dramatically impacted by asymmetries in the AMR grid, then it means that you need to make your AMR grid finer.
So I'm going to go back to the slides really quick to talk about our next problem. So we're going to look at IB explicit EX0. So this is one before. And this one has an exact solution. And the exact solution here is up there where the velocity is 0, the tension in the structure is perfectly balanced with the pressure. And so we're going to set the structure in its initial location. In fact, that's exactly what EX0 does. We set the structure in a circle. The force is the same force as we had before, but now it should be in its steady state configuration. What we expect to happen is for nothing to happen. And we'll see what happens. So now we'll go back out to the base build directory. And now we need to compile IBEX0. And hope that it doesn't take as long as it did last time. I thought it would be nice to have me compiling them at the same time as you did, but then it takes like 4 times as long now. So
do you need to plug your laptop in?
We're at 60% charge. We'll be fine. How's everybody doing?
Still don't have it built.
Oh,
That's okay. I'm emailing with David.
David's the one to contact. I have some of these pre-run, so don't worry. Don't panic too much. There it goes. So now we can go into examples, IB, explicit, EX0. And we're not going to go over the example.cpp, the source code, because of time constraints, but it looks exactly the same, except now the structure is set up in the code instead of via input files. So if you want to look at that, you can. We're just going to actually, I want to open up the input file, and what I want to do now, so I want to output the forces. So I'm going to change output F from false to true. So now with forces that are on our Eulerian grid will be written to our visualization files. So now when we run it, this also computes errors because we have an exact solution. But instead of looking at those, we'll just plot the solution and analyze it. We don't need to go to the end here either because we're set in our initial configuration. So I open up visit. So we open the viz2d file, look at the dumps file. Now let's plot the velocity magnitude. So we'll plot u magnitude. And again, we'll plot the structure. We already know we need to make the structure larger. And so again, so we've now set it up as a disk initially, or we're going to let it run. Oh, visit's really annoying sometimes. You have to make sure that dumps.visit is the active file for velocity to plot. Don't worry, you will all come to love the quirks that IBMR and visit have. So this is our solution that we get from IBMR, and we expected no velocity, no flow. Our exact solution was 0, and that the forces, the IB forces, should balance perfectly with the pressure gradient. But here we can see that we're getting a velocity field that has a magnitude of 0.02. That seems bad. Why is that happening? We can plot the forces. So this is the forces on the background grid. And you can kind of see that they look like they're normally pointed in. Well, let's go back to our slides for a second. One problem. Our divergences, our velocity is divergence free in the continuum sense. Discretely, our velocity is divergence free. But that doesn't mean when we interpolate our velocity with the delta function, that the discrete divergence of the interpolated velocity is divergence free. So that's one problem. Another problem is that we said that the force was equivalent to a pressure. It is equivalent to a gradient of a pressure. But when we, and so that's true in the continuous sense. In a discrete sense, once we replace our delta function with a discrete delta function, we are not equivalent to a discrete gradient. And so our delta function here can dramatically affect the results. If we can choose our delta function so that we maintain the important properties that our continuous or discrete operators have, then perhaps we can greatly enhance the accuracy of the problem. This is something that Boyce will talk about in more detail, but just to show you that effect, if we replace our delta function with these new delta functions, composite B-spline 5-4, and we run that same program, Maybe you can tell the solution. That's hard to see, but we can reopen these files. And now if you look closely at these velocity magnitudes, they're all 10 to the -6. So these are close to a solver tolerance. So we've dramatically reduced the error associated by 4 orders of magnitude hitting solver tolerance. So our choice of delta function can dramatically impact our solution. You have to carefully choose it.
What was the regularized delta function you used before?
IB4.
Okay, so why
Uh,
why was it? Sorry.
we will talk about this.
I'll talk about this afternoon. If people are interested in hearing about it, I have more material than I think I can cover. So we can kind of pick and choose a little bit. But one of the things that I have some details on is kind of like what goes wrong with IB4 and similar looking regularized delta functions.
Okay.
Or this
The traditional, I don't,
This is Charlie's 4-point delta function.
Cosine?
No, the one with moment conditions, and the sum of squares condition.
Yeah, that's
okay. So delta function is important. We can talk about slender body model, So this is something that Suk talked about earlier today. We also have support for that in IBMR. So the idea here, just briefly recap what Suk already talked about. We now introduce director vectors to so that our body can account for twist instead of just curvature and tension. So to do that, we have director vectors that you can put on the structure associated with an orthogonal representation of the local frame. We need to specify how they move. So that's our last equation that says that our director vectors are going to rotate the local angular velocity. So now we need to interpolate the angular velocity to our structure. That's not a problem. We already have delta functions that can do that. And we also need to account for the torque that's being applied to our fluid. And so we have to add in an extra torque that we spread from our structure back to our fluid. You have to specify what these fork and torque densities are. So showed similar ones. I think these are slightly different than what she showed, in particular the twist. But there's twisting energies, there are bending energies associated with it. So we're trying to hit a certain curvature of our structure and a certain bend, or a certain twist of our structure. And then we also have shearing and stretching. And then you can compute forces associated with those energies by taking appropriate derivatives. This is the default one that's put in IBM. So to look at the actual code associated with this, we're going to look at IB explicit EX4. And so now I am going to go to the source directory. So go to auto IBMR temp, unpack IBMR-0.16.0 samples explicit EX4. So now we have very similar files, except now we have, instead of a .spring, we have a .rod and .director. We'll look at those in a second. We want to pull up the example.cpp. Again, I'll start at the main routine. Everything here in the main routine, almost everything, is exactly the same. So we have kind of the same stuff that we had before. When we get to our important parts, we set line numbers. Line 141, again, we create our Navier-Stokes solver. So we need to solve the fluid equations. We again have our IB hierarchy integrator that can solve our IB equations. But the change here is that now we have a different IB method. We now have what we call the generalized IB method. So this will allow us to solve for those director vectors. But it functions exactly this, or the code looks very similar. We still give that way to compute those forces, a way to update the Lagrangian structure to the IB hierarchy integrator. Still have to give it the fluid solver. We still have the same patch hierarchy setup that we had before. The other difference here is that we have to give it the Kirchhoff rod model instead of the IB standard force gen. So a different way of computing forces. But other than that, the code is exactly the same. So swapping out kind of IB models is easy in that regard. Okay, so let's run this. So we go back to our build directory. I didn't go to the build directory. I've already built this one. I was smart and thought ahead for 2 examples. So now we have a poorly named main2D file. This is a 3-dimensional file. This is a mistake that should be fixed at some point. But now we have an input 3D file instead of input 2D file. It looks exactly the same, but everything has its dimension increased by 1. And so we can run this as before, but it's going to take a lot longer because it's 3-dimensional. So we're not going to let it run all the way. Fortunately, I came prepared and I reran this. So I can show you the results without actually having to run the code. So we'll open up Visit as we did before. Now we have a Viz 3D file. I've put the finished files in finished Viz 3D. So we have a 3-dimensional grid now that has locally refined areas. For now, I'm going to delete that and show you the lag data.visit because it contains the mesh. We have a 3D mesh, although it is initially 2-dimensional disk. So we can look at the director vectors. We can plot D1. We can plot D2. So again, these are our orthonormal set of director vectors that tell us the local twist of the structure. And so you can see that although the rod is initially flat in a circle, it has some twist associated with this. And so we've set this up so that it's trying to have a 0 twist. So we let this run. You can see it takes a little bit. Nothing interesting happens for the first 20 seconds. So what we can do is speed it up by skipping time steps. So we'll skip every 3. So something's about to happen, I promise. You can start to see it now. It starts to move, and it's trying to hit a 0 twist, but it's a closed loop, so it can't exactly hit a 0 twist. So it curls up on itself and makes a funny shape. It's the technical term for it, funny shape. And so anything else I want to say? So you can also visualize the Eulerian velocity fields and all of that looking at the dumps file, dumps.visit. questions about that so far?
I'm curious, is the final state here repeatable if you change the initial state a little bit?
Ooh, so do you know?
If you give different initial conditions, you may deform into different shape. It's very sensitive. Yeah.
But the answer to that was it is sensitive to the initial conditions.
Yep.
Well, I mean, it's sensitive to the number of initial twists, right? So I don't think it's very sensitive to the initial conditions, like the initial shape. You can perturb it, and I think it'll yeah. But you'll get different numbers of loops if you twist it more, right? Think about you've got a
along the circle. So two or one twist, two twist, three. So it'll give you a very different type of shape, like star shape or figure 8, or like three leaves. What is that? Clover shape.
Yeah, so you could think of this setup as like you've taken a rubber band and you've twisted it some number of times and you glue it on itself, right? Is the way to think about this. And then it tries to unwind and it can't. And in doing so, it creates these kind of multiple loops.
We're done at 3, is that right? So is 3 our cutoff time for this?
Yeah, I think we're supposed to go to 3.
So, but we have 12 minutes. Just enough time to do the last thing I wanted to mention. So I'm going to go back to the slides. So we also wanted to talk about, I also wanted to bring up different fluid models, because this is, again, a big difference between immersed boundary methods and regularized Stokes-Slip methods. And that it's, if you want to do something non-Newtonian, then regularized Stokes-Slips aren't easily set up to handle that without perhaps using discrete measures of elasticity. And so if you have a viscoelastic fluid, it will exhibit both viscous and elastic forces. And so you can think of a spring being a perfectly elastic structure. You stretch on it, you let it go, it snaps back. So its stress is linearly proportional to how much it's being stretched. A viscous element like a dash pot the stress is linearly proportional to how fast you stretch it, so the rate of strain. And so if we wanted something that was viscoelastic, we need something that has both of those properties. And so you could consider taking a spring or a dash pot, putting them in series or parallel, and you'll get something with different long-term behaviors. A Maxwell element at long-term behaviors will behave like a viscous fluid, like a dash pot. And so this is the model that we will focus on for the next example. So we take our Maxwell element, which has kind of a more complicated stress-strain relationship. We take the rate of strain, or the time derivative of the stress, replace it with a convected derivative, an appropriate convected derivative, similar to the material derivative for the velocity. But now this is a tensor, so it becomes just a little bit more complicated because you have to worry about how the stress tensor rotates. We take the rate of strain, replace it with the rate of strain tensor, and that is what we call a Maxwell model for a fluid. The Oldroyd B models says there's also an associated viscous solvent, so the background fluid. So a picture to have in your mind is, if we're thinking of a polymeric fluid that has viscoelastic behavior, the polymers are behaving something like springs or Maxwell elements, and they're immersed in water, which is behaving as a solvent. And so in Oldroyd B model, we have our total stress has a contribution from a viscous solvent plus a viscoelastic component coming from a Maxwell type model. And then of course you can get more complicated if you want to, but I don't want to, for now at least. So something like the Giesecke model has an anisotropic drag term representing drag that polymers might experience under flow. So I'm not going to talk about dimensionless numbers. I don't know this one. That's probably looks bad if I don't talk about dimensionless numbers, but so it goes. So this is our complete model, except now we have, instead of just our viscous component, we have an extra stress tensor that we have to advect around. So we have an extra component that we need to advect and diffuse, or really just advect, and that shows up in our momentum equation. So the example we're going to look at is examples complex fluid EX2. So I'll open up the source code for that as well. Maybe AMR, examples, complex fluids, EX2. And so this is going to look very similar to every other one. There's two big differences here. One, we're setting up a structure to be a finite element mesh. So this is a finite element structure instead of a point cloud. And so there's code in here that creates a simple finite element mesh of a disk. Oh, wait. This example is flow past a cylinder, flow past a confined cylinder. And so we want to put a cylinder inside of our inside of a channel. We do that by creating a finite element mesh. You could also similarly do this with a point cloud 1 and 2. And the second important part, we still have the Navier-Stokes integrator, but now we have an extra advection diffusion integrator. And we have to advect this stress tensor with the flow. And so this advection diffusion integrator knows how to solve advection diffusion equations. And so we create one and register it with a Navier-Stokes integrator so that it can use the fluid velocity that we are calculating. We still have the IB explicit integrator, IB hierarchy integrator that knows how to solve the IB equations, but now there's an associated IBFE, standing for immersed boundary finite element method. And this knows how to compute forces on finite element meshes instead of point clouds. And so there's a little bit of extra code where we initialize, before we initialized the forces, told it how to compute the forces. We also have to do that, but now in a finite element way using WoodMesh. The actual function that calculates the forces is called the tether force function. This is defined at the very top. So I can go and show it to you. This is the tether force function, computes a force, and that force is defined on line 81. This, you can think of this as a spring force that is tethering its current location, little x, to its initial location, capital X. So this is a spring force preventing or trying to oppose motion of the structure. And as kappa, our penalty parameter, gets very large, we will recover no motion in our structure. It's what we call a penalty method. So we can run this one. So we again go to the build directory. We need to make sure we compile complex fluids EX2. I already did it because I was smart and thought ahead. So now we go to examples, complex fluids EX2. And we can run main 2D, input 2D. However, to make this more efficient, I'm going to increase the Reynolds number to, instead of being 10 to the -5, to be 1, so that we can run this a little bit faster. And then there's an option here of divergence tagging, so we can tag the divergence of the velocity field and we'll set the defaults. And then there's vorticity tagging. We can tag the vorticity of the fluid. I will also set the defaults so that we don't expand or AMR structure. So now when we run this, we hit, wait, this was not the segment. Oh, yeah, there's a bug currently in version 0.16 that if you output the strain, you get a seg fault. So we can't output the strain, so we have to set output strain. Yep. So now we can run it. There's an important part here I want to hit. This one also takes a little bit of time because it's a very big domain. And you didn't set up AMR correctly. Well, to really refine things in an efficient way. You can put that blame on me. I wrote this one. Okay, so we hit an error. The structure has moved too much, right? We were trying to use a penalty method to oppose motion. And in this case, there's a flag in the code that says if the structure has moved too much, throw an error. So how do we fix that? Well, we can increase the penalty constant. So we can go into the model parameters. Kappa is our penalty parameter. You multiply it by 10, and then so you have a stiffer spring tethering to its initial location, and that will fix things. In this case, I won't run it because it's going to take a while and we're about to be done, but I will show you the final example.
Will it adjust the time stepping?
No. So the question here is, will it adjust the time stepping? So there is we're using an explicit method. You have a very stiff structure. You have to resolve the oscillations of that spring. You have to determine the time step. So it will not automatically adjust that time step. It turns out that if you multiply it by 10 in the way that this example is set up, this specific example doesn't have to adjust the time step. But in general, you have to do it.
You could have taken a larger time step before, right?
Yes. Okay. Well, we changed the run somewhere. So that's also going to change properties of everything. But yes. So I have already run this, and so we can plot now we have an exodus file instead of a lag data.visit because we're using a finite element mesh instead of a point cloud. The output is slightly different, but you can still create the mesh. We'll zoom in on the structure, and you can plot things on the dumps.visit. For example, the components of the stress. So this is one of the diagonal components of the stress. And you can see that there are stresses that appear on the top side of the cylinder. I think back here, I think she might be talking about this somewhat in her, maybe not. So there's a big question here. I just want to briefly mention this of accuracy. And this will be important, I think, for one of Boyce's things that Boyce may talk about is can you accurately resolve the stresses with the immerse boundary method? So you can compute convergence rates for the components of the stress. And this is this column in the top right. And point-wise, we do not see convergence in the stress. So you might say that's a deal breaker. Oh, here's my
Polymer stress or the
polymeric stress, and also the velocity converges at first order in the L infinity rate. So the velocity gradient, which is part of the solvent stress, will not converge. The velocity gradient doesn't converge. The components of the polymeric stress do not converge on the boundary. You can ask why that is, and that has to go back to, well, we used a singular delta function in our original equations. So we spread the force from a singular delta function. So if we integrate our momentum equation, the integral of a delta function is a heavy side. we integrate our momentum equation, that divergence of the stress goes away, so that we just have the stress is proportional to a heavy side function. So that tells us that the stress is discontinuous across the interface. This is a little bit hand wavy, but you can make this concrete. And I don't know if Boyce will make it concrete or not, but I hope he will. He will not. So you can read it in a paper to make it concrete. But you can show that the stress has a jump across the interface. And our regular finite difference methods only converge if our solution is smooth enough. Since we have a jump in the stress, do not expect convergence of the stress. So you have to do something about that. And that's what I call the immersed interface method, where you build those jump conditions into your discretization. And Boyce will talk about that? Maybe.
If people want to hear about it.
But you can ask, even though it doesn't converge point-wise, is that okay? And the answer is, well, if you care about average quantities on the surface, like a drag coefficient, we still get accurate first-order convergence. We get first-order convergence and drag coefficients. So as long as you care about averaged quantities, immersed boundary works very well for stress. And you have to do something if you want higher order convergence.
And in terms of the accuracy here, it is actually, as best as we can tell, it's pretty competitive with body fitted finite element methods for the same kinds of problems. So if you want to get kind of like net forces on these kind of structures, this is about as good as anything else.
What's PL?
PL, piecewise linear. So these are different kernel functions. You should maybe not be using these kernel functions, as we now know. But when we made this a few years ago, we did not know. So these were piecewise linear and B-spline kernels. Oh, there's a B-spline 3 here. In the interest of time, I'm happy to talk more about kernels, but I want to finish up, just conclude with, hopefully this was a decent introduction to IBAMR. We derived our conservation of mass momentum equations. We hopefully understand how to interpret the IB equations and where they came from. Maybe you can use IBAMR to explore the other examples. If not, I am here for the rest of the week, so we can talk about it.
Is there any documentation on which example is which?
No. There are some examples that have README files, but if you have a question that you're trying to model, we could probably point you to an example. But unfortunately, documenting the examples has been on the to-do list for 10 years now, and it has not been gotten to.
I think different groups have documented what some of these examples mean.
That is, yeah, maybe Mara might have documentation, or I guess by extension, Alex might have. So next, when Boyce gets up here, whenever he does, he's gonna talk about things. I don't know what he's gonna talk about anymore. I thought he was gonna talk about these things, but maybe he'll talk about something else. It'll be fun. So if you have questions, I'm happy to take them.